Today I will be discussing about directional stability, directional control, and then later on lateral stability and lateral control. You know by now longitudinal stability, and what was the understanding that if this airplane is flying, this is the tail plane, and if there is any angle of attack disturbance coming like this positive angle, then it will generate a lift, and this lift will give moment about center of gravity nose down. So, we say for a positive alpha, the tail is producing a nose down moment which is negative, and we say Cm alpha is negative. So, the contribution of tail is towards making the aircraft statically stable in the longitudinal plane, right. Today, we will be talking about directional stability, and what is the directional motion? If this is the airplane, let us say, and this is the x axis, this is the y axis, and this is z axis, then directional motion is about z axis like this. Okay? And we will see that this horizontal stabilizer was helping for longitudinal stability. Now, this vertical stabilizer, this whole vertical stabilizer will help to give directional stability, and as in longitudinal case, elevator was giving longitudinal control, that is when I was pulling the elevator up, the airplane also will pitch up, and when I was putting elevator down, the aircraft also will pitch down. So, we are discussing this in terms of longitudinal control, and this is the elevator control. Similarly, for directional case, you could easily see if we deflect the rudder this way, an airplane is moving in this direction. So, it will generate a force in this direction, and that force will give a yawing moment taking the nose towards left. And if I do it like this, then the force will be towards me, and this will give a yawing moment which will take the right wing back, right. As far as convention is concerned, we will assume that, which everybody has following this convention, that when I am flying like this, rudders toward left is a positive rudder deflection, and rudders towards right is a negative deflection. So, keep this back of your mind. Now, we will go to the classroom and we will discuss in detail. We have just now seen the vertical tail, or you call vertical stabilizer, and also a rudder, and the purpose of today's discussion will be on directional stability. If I draw the diagram for the axis system, this is x, this is y, and this is z. And we know that when we are discussing longitudinal stability, longitudinal static stability, we are talking about motion about y axis, that is pitch up, pitch down. But now, once we are talking about directional stability, we will be talking about motion about z axis. And the convention is, if these are the two wings, if the right wing going back, the yawing moment is positive. That is, if right wing going back, that convention wise that will be yawing moment positive, and left wing going back is yawing moment negative. What is the yawing moment? Yawing moment is the moment about z axis, right. So, as far as yawing moment which is about z axis, and convention by positive if right wing going back while flying, going back, right, and this is negative when you see right wing going back, yawing moment positive, and when left wing going back, this left wing going back, then yawing moment is negative, right. Who causes this yawing moment? You can understand that if some motion has to be there about z axis, then the force has to come like this, right. So, for example, if I take this case, if I see vertical tail or vertical stabilizer, and this is the airplane, suppose like this, and z is here. So, if it has to turn like this, that means some force has to act here, right. So, vertical stabilizer will play that role, will generate yawing moment, which will try to help in giving static stability in the directional case. But always remember one thing, this directional case, that is motion about z axis and the motion about x axis, they become coupled. No? How it happens, you see? You could see when I am yawing, we are discussing about directional motion and try to see the directional motion and lateral motion gets coupled, right? Think these are the two wings. If I am giving a positive yawing moment, that is right wing going back, see what is happening at the wing. This wing is seeing lesser velocity because I am moving forward, but the wing is going back. So relative airspeed here is less, whereas relative here in the left wing, on the left wing is more. So lift here will be more. So naturally, if lift here is more compared to this will also bank. So that means what is happening? As I am yawing, I automatically get banked. So I can say the directional motion and the lateral motion, they get coupled. But we will be now studying directional stability separately, then lateral stability separately, then we will discuss about their coupling, etc., etc. Okay? This thing will not happen for longitudinal case. For a small rate or small change in angle of attack, it will not influence anything about other directional or lateral case at small angle of attack. Okay, so let us come back to directional stability. What does it mean? We have to define something called side slip angle. For example, suppose this is the path and the aircraft and this is the velocity direction and this is the fuselage reference line. So now the relative air speed, I can write it as if it is coming in this direction. Right? When I say relative air means it is relative to aircraft, right? So now what is happening? Actually the airplane is moving like this, okay? Not like this. For normal case, if I am flying a machine, I am going like this. But here, actually if you see, instead of this, I am actually going like this. So this angle, beta, is called side slip angle. Is it clear? I repeat again. If this is the line, center line, and if I am flying like this, and relative air is coming like this is the axis, this angle is beta, which is called side slip angle, and this will have an effect on the directional stability. We will see how the airplane gives a response to such beta, such side slip angle, to ensure that it is having some sort of a static stability in the directional case. Right? Now this beta is, let's say I call side slip angle. Soon you will realize that how important is vertical tail to ensure that it does have static stability in directional case. So let us try to understand what is the meaning of static stability. We have seen that static stability means if a body is disturbed from its equilibrium state and if it has initial tendency to come back to the equilibrium, then you say the body possesses static stability. Okay? Now, let us say this body was flying like this, beta equal to 0. Mostly the pilot will fly a machine at beta equal to 0. So for all practical purpose, beta equal to 0 is the equilibrium state for an airplane. There are some one or two occasions during especially landing or when you try to reduce the speed, increase the drag for some specific purpose, that also you will come to know the pilot may tend to fly at a particular yaw angle or particular side slip angle, more accurately side slip angle. It is not yaw angle. Yaw angle by convention is different than side slip angle, which we will be discussing as we go forward. Let us talk only about beta, and that is side slip angle. So if a pilot is flying at beta equal to 0, and let's say there are some wind coming from right hand side. So this will make the relative airspeed this way, and so this will introduce a beta. But what is the equilibrium? Equilibrium is beta equal to 0. So if the airplane has initial tendency to come back to beta equal to 0, then what the airplane should do? Airplane should immediately generate a yawing moment like this, right wing going back. Then only beta will become 0. Am I correct? Is it clear? So it should, for positive beta, it should generate a positive yawing moment. Why positive yawing moment? Because we know that as per the convention, right wing going back is positive. Right? Let us understand this concept little more clearly before we go to next step. We have just introduced something called beta, which is side slip angle. We have introduced symbol beta, which is side slip angle, and I have told you, be careful, this is not yaw angle. We will define yaw angle later. At this point, we only restrict to beta side slip angle. And what is the side slip angle? This is the airplane. The top view I am taking. This is the central line. And if the aircraft CG is moving in this direction, so it is moving like this. The airplane is moving like this. Okay. So this angle is beta, and beta is positive, convention-wise, when you are flying the machine and the relative wind is coming from the right-hand side. Okay? So relative wind from right-hand side. Okay? So what will be the beta negative convention-wise? Beta negative will be other way, if it is like this. That is beta negative. Now, you know the most of the time, beta equal to 0 is the equilibrium. So suppose I am going at a beta equal to 0, and suddenly there is a disturbance that has introduced beta. So if it has initial tendency to make it to beta equal to 0, we say it is statically stable. That means it has to turn like this. Turn like this means right wing going back. That means it has to generate, for a positive beta, it must generate a positive yawing moment. Okay? That is clear. Similarly, for negative beta, it should generate negative yawing moment. Right? Remember, for longitudinal case, it was for positive alpha, longitudinal case, positive alpha, the pitching moment was negative to make it statically stable. But for directional stability, we are seeing for positive beta, it should generate positive yawing moment, right? So if I'm going like this, and suddenly some wind disturbance has come, which has given a beta, so I should be able to turn like this to make beta equal to 0, and then only we say this aircraft has directional stability. And we'll also discuss how much directional stability is required as we develop our lecture, right? If this is clear, so now see how to design an airplane so that this phenomena can happen. So what we have seen for static stability, for positive beta, it should give positive yawing moment, and for negative beta, it should give negative yawing moment. And generally by notation, we use n for yawing moment. Okay? And similarly, we will define Cn, yawing moment coefficient, by n by half rho v square s and b. See, this is moment, so this is the force and this is the length term. For longitudinal case, we are using mean aerodynamic chord as that length to be used for non-dimensional. We are using c bar as a length to non-dimensionalize pitching moment, but for non-dimensionalizing yawing moment or roll moment, you will see we will be using b, that is the span of the wing, right? Wing. Okay. So this is Cn, which is also called yawing moment coefficient. Like for longitudinal, we had pitching moment coefficient Cm. For directional case, we have Yawing moment coefficient Cn, and as we have understood, for static stability, for directional static stability, we have seen for positive beta, Yawing moment should be positive, so I can write Cn should be positive. Similarly, here Cn should be negative. Okay, anyway, Cn and Yawing moment are related like this. So if I write Cn here and beta here, and equilibrium is at beta equal to 0. So if I draw it like this, do you think this will have static stability? Check here. For positive beta, Yawing moment should be positive, or Cn should be positive. For positive beta, it is negative. So this is wrong. This is not correct. So what should be the correct thing? If I draw this is as Cn, this is as beta, then correct thing should be this. Equilibrium at beta equal to 0. Now you see for positive beta, it should give Cn positive. So Cn positive is coming. For negative beta, Cn negative, this is coming. So what is the meaning of this? Its meaning is dCn, the slope of Cn versus beta should be greater than 0 for directional static stability. Clear? Please recall this sort of a slope negative was there for longitudinal case, for which Cm alpha was supposed to be less than 0. But for directional case, Cn beta has to be greater than 0. That keep back of your mind. Okay? So this is the condition for directional stability as far as static part is concerned. So now see who are going to contribute towards this. As all the time we do, Cn beta I can get from vertical tail primarily, I can get from wing, I can get from fuselage. Let us see first the contribution due to vertical tail. Okay? I am making a simplified diagram. This is the center of gravity of the airplane, and let's say this is the vertical tail, and this is the AC of the vertical tail, and let me write this distance as LV, that is distance between the AC of the vertical tail and CG of the airplane. For longitudinal case, if you recall, we used some term called LT, and what was LT? LT was distance between AC of the horizontal tail and CG of the aircraft. But now I am using a different nomenclature LV for vertical tail, because it is not necessary that horizontal tail AC and vertical tail AC will be at same point. There are very configurations where I find horizontal tail is like this and vertical tail is somewhere here. So they can be laid out differently. So in general, I am using a term, a notation LV as length between CG of the aircraft and AC of the vertical tail. Right? And I also know, as per the sign convention and axis convention, this is the X, this will be the Y, and this is the Z. This is a body fixed axis. What I want to see, please come back here. We want to check if there is a beta disturbance given to this vertical tail, whether it will generate a positive Cn or not. If it generates positive Cn, that means Cn beta, because the vertical tail is positive. So I will say the vertical tail is providing directional stability to the airplane. Right? So let us see, let us give a positive beta to the vertical tail. And you know positive beta means the wing, if I am moving like this, the relative wind should come from the right hand side. So this is a positive beta. What will happen if there is a positive beta? Let us also see. Let us see, this is the vertical tail. Okay? Vertical tail. I was moving like this. Now suddenly there is a wind, crosswind coming like this, because of the relative velocity, relative air velocity has become like this. So this is a positive beta configuration, because relative wind is towards my right. Now what this beta will do? This air will give a force on the vertical tail in this direction. Ideally, it will be perpendicular to the velocity vector, but if this is small, I can say it is something like this. What this force will do? This force will, CG somewhere here, this force will give a moment which will take right wing back. So indeed, this will make yawing moment positive. So vertical tail will give adequate directional stability. And let me repeat, if there is a positive beta, this will give force here, and about CG, it will give a yawing moment which will take right wing back, so that Cn is positive, and if we design properly vertical tail, we can get adequate directional stability because of vertical tail. If that is the understanding, let us try to formulate it. Okay. Let us see for a beta what is the force in the y direction. Okay. We are assuming small beta, so force will be half rho v square at the vertical tail, dynamic pressure at the vertical tail, is vertical tail, and Cy because of vertical tail. Like you have Cl, and here we have Cy. I put V to ensure that it goes to your mind, it is because of vertical tail. So you can see from a Cy is nothing but force Fy divided by dynamic pressure into area, reference area. It will come if we are doing it for overall airplane, but it is for the tail, so we are writing as V, right? Now, what happens? This force will do what? This force will give force in this direction. I have just demonstrated. This will give a yawing moment positive. So yawing moment will be given as this Fy, that is half rho v square vertical tail is vertical tail Cy into Lv. Right? We have to ensure that in this, the yawing moment, whatever we are calculating, it should have appropriate sign. Now, to ensure that sign, we will have to do little more work, because this sign convention, etc., we have defined, so we should be very, very careful. So what is Cy? Let us see. So if I want to ask you what is Cl, we write Cl alpha into alpha, assuming Cl naught is 0. So what is Cy? Cy I will write Cy beta into beta. Correct? Okay? That is, if I make it more elaborative, dCy by d beta into beta. Like this was dCl by d alpha into alpha for longitudinal case. Now let us see what is the sign of dCy by d beta. That is important. You could see that for a positive beta, this force Cy will be in the opposite direction of y. If this is the y, the force will be in the opposite direction. If I demonstrate here, you see this is the x and this is the y towards you, and this is z. Positive beta is like this. This will give force in this direction, which is opposite in the direction of y. So positive beta will give you negative force as far as axis system is concerned, because y is towards you and positive beta, the force is in this direction. So I have to take care of that sign here. So what I do, I say, I can understand from here, the sign of Cy beta is less than 0. Because for a positive beta, the Fy is negative. Because why this is less than 0? We know for a positive beta, Fy is negative, and it is negative, and Cy is Fy by half rho v square s. And of course, Cy beta means just take one derivative. So naturally, if this is from here, if Fy is negative, then Cy beta automatically becomes negative. Correct? Which physically also you understand. I repeat again. I will take this register for you to get more clarified. If this is the vertical tail, and assume that this is the y direction, because this is x, y, and if beta is coming like this positive, that will give a force in this direction. So it will give a negative in direction as far as force direction is concerned. So for a positive beta, the Cy becomes negative, or we say Cy beta is negative. Okay? Please do not get confused with Cn beta. This is Cy beta. So now if I want to see this yawing moment here, I further now go into little bit of detail to ensure the signs are consistent. So then I write yawing moment is equal to half rho v square dynamic pressure vertical tail, S vertical tail, and for Cy I write Cy beta into beta into Lv, which is the vertical tail arm. Now, if I write it like this, since we know Cy beta is negative by definition, the way we have defined, so then this tells you that if beta is positive, then Yawing moment becomes negative, but which is not correct. For beta positive, although Cy become negative, but it is giving a positive Yawing moment. That is, please understand again and again, I am repeating this. If this is the vertical tail, beta is positive, Cy is negative, but this is giving a moment, right wing going back, Yawing moment positive, right? So, to ensure that you are getting Yawing moment positive, you have to put here minus sign. Now, you see what happens. If beta positive, Cy beta is negative, and this minus sign is there, this gives Yawing moment positive. So, from here, if I write Cn, Cn will be Yawing moment divided by half rho v square S reference B with the span. So, this will become, you are not expert, neta the ratio of dynamic pressure at the vertical tail and by half rho v square free stream, then SV by S you will get, then LV by B you will get, then Cy beta into beta, and of course, you have to put a minus sign here, right? And then what is Cn beta? It is very clear. So, using this Cn expression, Cn beta is linear, you have to just divide by beta here or differentiate. So, Cn beta will be equal to dCn by d beta, which will be equal to minus neta SV LV by SB into Cy beta. Am I correct? SB LV. Right. So, what is the sign of Cn beta? Here, this Cn beta is because of what? It's because of vertical tail, right? So, this is because of vertical tail or vertical stabilizer. This sign will be what? Will be greater than 0, because I know this man is negative, this is positive, this is negative. So, this is positive. So, indeed, vertical tail or vertical stabilizer, they are stabilizing directionally. Correct? And you could now see what is this SV, LV by SB. Does it help you in thinking something similar happened in longitudinal case? That was ST, LT by S C bar. So, it is that time that was called horizontal tail volume ratio, and this is called VV, that is vertical tail volume ratio, tail volume ratio. You could see that this VV, this whole expression is so important. If I increase the value of VV, I can increase the contribution of vertical tail towards directional static stability. What is the meaning of increasing this expression or this value? That you have to either increase the vertical tail size or increase the length of its placement from the CG, or doing both. So, this is another very important design parameter when you are designing an aircraft. So, just now we finished the expression for Cn beta vertical tail, and we see that it is having stabilizing effect on the airplane directional stability. Is it clear to everybody? Okay. Another important thing for longitudinal case, another important thing you must take a note for a longitudinal case, if there is a wing here and here there was a tail, horizontal tail, then because of the downwash, the angle was, whatever angle it is being seen, minus epsilon, downwash angle, right? We know about this by now. But for an airplane having a beta, that means the relative wind is coming like this, Okay, that is why beta it is. Suppose this is the fuselage, we are moving in this direction. So the vortices will now be at an direction along the velocity vector, relative velocity vector. So this will give some sort of a side wash. It is analogous to a downward. It's called side wash and denoted by sigma. And the angle of attack at the vertical tail, which was beta, now it changes to beta plus sigma. Okay? What is sigma? Sigma is the side wash. Right? There are empirical ways of finding sigma value. Okay? So now what is happening? So what is the force? So the Fy will be equal to half rho v square at the vertical tail, S vertical tail, into Cy beta into beta plus sigma, right? Because now because of side wash, this angle seen is beta plus sigma. So the force will be half rho v square Sb Cy beta into beta plus sigma. But note down, we have agreed that for a positive beta, the Fy should be negative. But I don't see any negative sign here. But you know that Cy beta is less than 0. So that is taken care from the value of Cy beta. So if I put Cy beta value say minus 0.3 or minus 0.6, the Fy will be negative. Okay? Now from here, for your clarity, Yawing moment about Cg will be half rho v square vertical tail S vertical Cy beta into beta plus sigma. So from Yawing moment, how do I come to Cn? You know that I have to divide Yawing moment by half rho v square Sb. So I divide it by Cn equal to Yawing moment divided by half rho v square Sb, b is the span. So this becomes half rho v square at vertical tail. This is the dynamic pressure at vertical tail into Sv into Cy beta into beta plus sigma. Before I write in the Yawing moment expression, don't you think there is a mistake? Half rho v square S Cy beta into beta is the force. But I am talking about Yawing moment. So moment would be what? This is the force here, Fy into Lv. This distance should come Lv. That so this term was wrongly written. So we correct it. We write it Lv. Lv is the vertical surface tail moment term. Okay. Now I am correct. I write Lv, and this is divided by half rho v square free stream. You know by now, S and B, the non-dimensional length has to come because it is a moment. This is force into distance the moment. And now if I write the expression, I get Cn equal to neta Sv Lv by Sb into Cy beta into beta plus sigma, right? See, I have taken Sv, Lv, S and B. So this is by this is neta. So Sv, Lv, S by Sb. This is here. Cy beta here, beta plus sigma here. What is our aim? We want to find an expression for Cn beta because we want to ensure that Cn beta is greater than 0, and we are talking about only vertical tail contribution. Right? So what will be Cn beta? So dCn by d beta will be neta. Let me write this Cy beta into 1 plus d sigma by d beta. What is the sign of Cn beta? Cn beta is positive, right? But now what is happening? If I go like this, I know Cy beta sign is negative. But this shows that I have done something wrong in the expression. What is that wrong? Let us go back and see. Because this is extremely important for keeping the sign into mind. Let's see here. This beta was giving Fy. So Fy is here half rho v square Sb Cy b beta plus sigma. we have seen for a positive beta, Fy should be negative. So, and we know that Cy beta is negative, so taken care Fy is negative. Now, from here when I come into moment, please see, for Fy, for whatever Fy we are getting, it should give me a positive Yawing moment, right? If you see this is the vertical tail and Cg is somewhere there, if there is a beta, force is here, that will give a moment, so that right wing going back. Now I have to see whether I have taken that into care or not. If you see y m is the Yawing moment, and I know Cy beta is less than 0, so then whole expression is becoming negative, which is not correct, because I know from here, if Cg is ahead of vertical tail, which is true, this beta will give me a moment, Yawing moment, where right wing going back. So I have to take care of that. So I have to artificially put a minus sign here. Please note down, this is extremely important, right? So that minus sign will also continue here, and this minus sign will also continue here, and minus sign will continue here. Is it clear to you or not? Please, let's go again. We know that for a positive beta, this Fy will generate a positive Yawing moment. But when I'm writing Yawing moment expression like this without minus sign, you know Cy beta is already negative, we have seen that. So without minus sign putting here, this will give me Yawing moment negative, which is not correct. For a positive beta, I should get positive Yawing moment, this right wing going back. So I have to put a minus sign here. And that minus sign should carry. And finally, I get an expression dCn by d beta as this. And let us have a closer look on this expression. What expression I got is Cn beta is minus neta VV into Cy beta into 1 plus d sigma by d beta. Okay. What is V? What is this? Could you recall similarity of this expression with longitudinal case? This is S vertical tail, L vertical tail by S wing and B span. So this is, if I try to find some sort of similarity for longitudinal case, we had VH, which was ST, LT by SC bar, and this we used to refer to as horizontal tail volume ratio, right? Horizontal. So what is this then? This is also, instead of ST, horizontal tail, this is S of vertical tail. Instead of tail momentum of the horizontal tail, it is vertical tail. And S is the wing area, and B is, for a convention, which everybody follows, we have taken span instead of C bar. So this becomes what? This is again tail volume ratio, but for vertical tail. For vertical tail. Very clear? No doubt about it? Now, what was the role of VH? VH was, you know that this was primarily giving the longitudinal stability through the horizontal tail. If tail volume ratio is higher, then you will have more and more static stability. Similarly, here you see, we wanted Cn beta to be greater than 0, and you have seen that although minus sign is here, as per our convention, we know that Cy beta is negative, so this dCn by d beta is actually greater than 0. So for a positive beta, it is Cn beta is positive. That means it is, this vertical tail is giving directional stability. Okay? And who decides that? Not only Cy beta, it's also decided for a designer, it is the vertical tail volume ratio. So you can appropriately select vertical tail area or vertical tail moment arm. I can put the vertical tail forward and aft, or I can, in a combination, I can increase VV, and if I increase VV, that means it will add towards more and more directional stability. Okay? So let us go a little deep into this. Cn beta greater than 0 ensures directional stability. We are talking about static stability. We are talking about static stability. Now, what is the issue you see? Next question comes to our mind, how much directional stability we want? we know that if we make it very high in terms of static stability, then if you want to change from one equilibrium to another equilibrium, there is a problem. There is a lot of effort is required. We have clearly seen in longitudinal case. But see here what happens. If Cn beta is very, very large, if Cn beta is very large, so far, please take a note, we have only computed Cn beta because of vertical tail. And because we know that primary contributor to directional stability is vertical tail, you will soon see that there will be contribution from wing and fuselage. Mostly fuselage will be destabilizing. Cn beta you see for fuselage is mostly destabilizing. We will do that. Cn beta from wing, you will see if there is a sweep, it is stabilizing marginally, stabilizing marginally. We will see these things just for a continuity, keep this back of mind. If Cn beta is very large, what will happen? So if Cn beta is very large, physically you see, if I am flying a machine and Cn beta is very large means what? The moment there is a beta disturbance, that means if there is a crosswind coming, it will have an initial tendency to nullify this crosswind effect. Okay? So that means if Cn beta is very, very large, the airplane will become highly sensitive to crosswind. If wind is coming like this, it will turn like this. If it is coming from right, turn like this. So the airplane will become highly sensitive to crosswind. That's not a good design. Right? So there will be a debate on how much Cn beta or how much directional stability I need to have. That will be a very important question before we try to understand what is the directional control, how a rudder will control vis-a-vis the directional stability of the airplane. That is, if Cn beta is very, very large, then you have to put a lot of effort on rudder to control this airplane at a particular direction, okay, or particular equilibrium. Right? Thank you very much.